We are going to discuss the beautiful philosophy behind Euler's theorem and some relevant ideas related to JE as well. So Euler's identity is a reincarnation of a very famous polar representation of a complex number. And just to recapitulate, as we have already seen before, if we have got a complex number z, it can be represented as a point x plus iy. And in polar format, this complex number can be represented as a distance r and the angle theta that it makes with the positive x-axis and anti-clockwise sense. So hence x is going to be r cos theta and y is r sin theta, which makes complex number written in the form cos theta plus I sin theta. We have seen already in the previous lecture what will be the implications of multiplying two complex numbers and dividing them. Now we are going to see a cool representation of cos theta plus I sin theta. So cos theta plus I sin theta, can it be written in a cool way? First way to discover, like, can we package cos theta plus I sin theta in a better way, is let x be this. Now maybe we are tempted to differentiate this because we know like cos theta differentiation is gonna give me minus sin theta and sin theta differentiation is gonna give me cos theta. So why not, if I differentiate, maybe like cos and sin is still we can restore in the system. So dx by dt is going to be minus sin theta plus I cos theta. Now you can take I common and we are having cos theta plus I sin theta, because it's I and cos theta plus I sin theta by definition is x. So what we got is dx by x equals I d theta. Now if you wonder like, can we differentiate this complex number and what does it mean to even differentiate I as if we are treating I to be just a constant, of course you can push forward the same law at least and break the laws of numbers and to put. Okay, so now you might have a confusion like, is it really sensible to differentiate a complex number? Of course you can do so, because after all we are mimicking the ideas of a real number in the entire discovery of complex numbers. So let's do and let's see like what discovery we make. Once you get some answer, we'll try to make sense of it from other field of mathematics, and once each and every field of mathematics agrees on a particular point, so that discovery will be validated as long as there is no contradiction in the statement. So dx by x equals I d theta. If we integrate, we are getting ln x equals I theta plus some constant. To be more specific, you'll get like ln mod x. So I'm not taking that. So x is e to the power I theta plus c. So even casually we can see we have one arbitrary constant c here picture. The initial equation was x equals cos theta plus I sin theta. So here if I'll keep theta equals 0, we are going to get x equals 1. So the boundary condition is theta equals 0 gives x equals 1. Because theta 0 will give this as 1 and this is going to be 0. So hence x will be 1. And that gives you x1 at theta 0 plus c implies 1 equals 1 plus c, hence c dies, and which tells us c is 0. So x we got another beautiful representation as e to the power I theta, and this is very cool way of restoring the information from cos theta plus I sin theta. So now we have the Euler discovery, e to the power I theta can be written as cos theta plus sin theta, the crazy mathematical discovery. With this discovery, let's play a bit. So for theta equals 0, we have e to the power 0 is 1 plus I times 0, which is 1, which clearly makes sense. If we keep theta equals, let's say, pi, then we'll have I pi equals cos pi plus I sin pi, which gives 0, and cos pi is minus 1, which is negative 1. But what we are getting, e to the power I pi is minus 1. It means e to the power I pi plus 1 equals 0. And that's really crazy. It feels so awkward to get this. because E is 2.71 something something, I is root minus 1, pi is 3.14 something something, and you are adding 1 to this and you are getting nothing as the answer, right? And this is the craziest discovery made by Euler, which is, you know, like one of the special case of this Euler's theorem, Euler's identity. It feels crazy for obvious reason, because 2.71, how someone can even raise to the negative like imaginary powers? It doesn't make sense. E to the power 2 makes sense into E. E to the power even 1 by 2 makes sense, you are root E. Okay, so and so on and so forth. But what even e to the power root minus 1? It doesn't make sense. It feels really nonsensical. What's crazy about this result is you have e to the power I pi that goes to 1. So is there any way to visualize this result? Okay, so let's try and attempt to visualize e to the power I pi. So for this, let's go back to our basic world and let's little bit talk about the exponential function. So you know, e to the power x, if I'll plot with respect to x, as x is 0 we have 1, at x is 1 we'll get e, at x is 2 we'll get e square, x is 3 e cube, so it's increasing too rapidly, right? When x is minus 1, it's 1 by e, x is minus 2, 1 by e square, x is minus 100, 1 by e to the power 100, so almost it is in ICU. So the growth is rapid growth. Rapid in the sense, if we'll take this y equals e to the power x, its derivative is still going to the e power x, and that's crazy thing. It means at x equal to 0, if you see the growth of function, at what speed the particle is moving at that point. Imagine if there is a particle which is moving along this curve, obeying the rule of the game, like its velocity is proportional to e to the power x at a distance e to the power x. So at 1, it's moving at speed of 1 unit per second. At a point 2, it's moving at the speed of e squared unit per second. At 3, it's moving at a speed of e cube unit per second. So you can see how fast it's moving. And let's say at some minus 100, it was too slow. At minus 1, it was still slow at 1 by e. So in fact, velocity vector itself is growing too rapidly. So this is what velocity lines will try to behave, right? So far so good, because that we can, it's a realistic situation where if I model this displacement as a function of time as e to the power t, we'll see something like this, and the velocity s dot t will still be e to the power t. Now let's see what exactly it represents in a Cartesian frame. So let's call if displacement at any time of particle is e to the power I theta. So what exactly I mean here? So we have a Cartesian frame, like now we are in 2 dimension. At t equal to 0, the particle was at this starting point A. That is the point which corresponds to t equal to 0, because you will get s equals 1. So that point is 1, 0, right? At t equal to 0, you are at the point 1, 0. Similarly, if you see what was the speed at t equals 0 for this particle, ds by dt, in terms of complex language, it's I times e to the power it. So at t equals 0, what is the speed? It's nothing but I. What is the significance of I? Significance of I means it's 1 multiplied with I, because as you know, any number multiplied with I will get just rotated by 90 degree, flipped by 90 degree. Anti-clockwise sense, right? So the significance of a speed I at t equal to 0 means you have a speed vector which is perpendicular to this, because this guy is 1, so 1 into y will be perpendicular. So at this moment a speed was perpendicular to this. Now if you think in a just a split of second, or just after a small time interval, let's take the gapping of t equals 0 and t equals 0.000001 second, what's going to happen? When t equal to 0.0001 second, the particle has moved to a new position, right? Which is given by, simply you'll plug it, you'll get e to the power something. So actually particle has tried to move, you can more or less assume it to be a straight line motion. In fact, it will be some curve, whatever it is. So this motion can be assumed to be a straight line if this gap delta is tending to 0. Okay, so for the sake of visualization, I'm taking a small gap of 0 and 0.00001 second. So at this point, when the particle just moves slightly, at that point, if we'll calculate the velocity, now you know it will be I times the displacement there. So if displacement is here, so this is a new displacement by this black line. So now the particle will try to move along a new direction with the same magnitude, right? Again, the particle will try to move along this in a split of second. Now you have a new displacement here, and particle will try to move now along again perpendicular direction to its displacement, and so on and so forth. Let's take one more position with another color. So let's say particle moved a little bit here, and now it's trying to move still in a 90-degree direction. Okay, so clearly from here it can be seen that the locus of the particle, the movement of the particle is going to be circular, because the particle is moving in a curve such that at every moment of time, its velocity vector is tangential to its displacement vector. So it must be pure circular motion. And that solves the problem magically, because if I ask you what will happen to the particle at t equal to pi second. So at t equal to pi, the particle have rotated exactly half semicircle. It has covered a semicircular distance. So this is the location corresponding to t equal to pi. Okay, and at that point the particle velocity is completely directed downward. So at t equal to pi, particle is at the position of -1, and that justified. So hence e to the power I pi becomes -1 visually with this physical concept, right? What will happen after pi? The particle still continues to move along a circle. So now you know, like there is a circular connection of e to the power it. So e to the power it has got some circle connection. Basically, circle is related to pi, so kind of e to the power it is pi connected, right? It's pi connected. And now we know, since particle is moving on a circle, so if I'll pick up any moment of time t, the angle that it's making, because initial distance was 1, so it's moving on a radius of 1. So theta equal to L by r radian, if length of arc. Speed of particle we are making the same unit, so the length of arc itself will be t, right? Here, according to this problem, because velocity and time relations. So here we can see, like at any point, the coordinate of the particle p can be given as cos theta, comma sin theta, which is basically in this specific example was cos t, comma sin t. Now in the language of complex number, it can be written as cos theta plus I sin theta. Okay, hence it's justified fully at any moment time t, e to the power it represents its new position, its new configuration. That's basically how much arc movement was there. So I hope it is clear. There is still third view of understanding this Euler's formula. So third view, and that can be done by a usual typical Taylor series. Although Taylor series expansion, I personally don't feel much satisfactory, for the obvious reason, like we are extending the Taylor series forcibly for even complex numbers, and there is no reason why it should be done at least at the first place for dummies, right? So we know like e to the power x has this Taylor series expansion. You can watch the separate video on this. What is the birth of e and these things. Okay. So in logarithm, I'll be discussing from where e is born out and why it's so useful. So it's basically infinite series. The essence of this series is, if we'll take e to the power x graph, and let's take the first term 1 plus x. So 1 plus x will try to, like haunt e to the power x slightly for some time, because at -1 will be 0. If we'll take 3 terms, the approximation of e to the power x will be very weak. If we'll take 4 terms, then maybe it will try to be closer to e to the power x for a quite good decent number of time. If I'll take 4 terms, the graph will be now more closer, and so on and so forth. E to the power x. In fact, for odd number of terms, it will go down, and for even number of terms, the graph will do like this, right? So fundamentally, what does it mean pictorially? If we'll take infinite terms, then e to the power x will exactly resemble. So what does it mean? Fundamentally, if we'll take infinite term, e to the power x graph will exactly merge with the graph of RHS. Okay, so there will be, the error will almost be tending to 0. Anyway, now since we are trying to mimic the concept of imaginary number by pushing forwards the fabric and the structure of real numbers, so here also no one can stop us, and let's put x equals I theta. This itself is a great question, like, is it really that we can? So this itself is a great philosophical question, like how someone can put x as an imaginary number, or a number which at a first say, let's say, doesn't make much sense. Clearly, if you see the proof behind Taylor series expansion, it doesn't require fundamentally, okay, like the realness properties, because the mechanics of differentiation still holds even for the complex numbers. Anyway, so if someone plug I theta here instead of x without even bothering about what it means, so we'll get 1 plus I theta is square by 2 factorial plus I theta cube by 3 factorial, and so on and so forth, and which accounts to 1 plus I theta, and this becomes minus theta square by 2 factorial. We have minus I theta cube by 3 factorial plus, and so on and so forth. And you can simply collect terms. Theta square by 2 factorial will have plus theta 4 by 4 factorial, and so on, and plus I times theta minus theta cube by 3 factorial plus theta 5 by 5 factorial, and so on and so forth. And by definition of Taylor series expansion, this is nothing but cos theta definition, right? You can check also at theta 0, this is going to be 1, so it's cos theta, and this is I sine theta series expansion. So that's another way of deriving this Taylor series expansion. Personally, I feel like it's fine, but this feels more cosmetic. At least the second method of visualization was quite natural way. Even the first way was a bit satisfactory. So to make it more satisfactory, let me tell you what exactly is happening when we are adding these terms, right? So when we are adding 1 plus I theta, what's happening? So let's say, if you look upon these terms like, like theta square by 2 factorial, theta cube by 3 factorial, and so on. So how do we look like? So what exactly this Taylor series is telling is this. Let's say if you have got an origin O, let's mark this x-axis. Let's say if you have got an origin O, let's mark this x-axis with different colors. So I'm cutting a length of 1 over here. Let's start with some angle theta. Let's call this represents theta. So let me use different color. So, and this represents theta square by 2 factorial. Maybe this color represents theta cube by 3 factorial, and we have other color theta 4 by 4 factorial, and so on and so forth, right? So what exactly this Taylor series is revealing us is this, and let me use other color 4. Okay, so we have this one, right? So what is Taylor series expansion is telling you is 1 plus I theta. So let me use different colors for this, and you can clearly see I've taken a number line where I have marked 1, and this gapping is theta square by 2 factorial, theta cube by 3 factorial, and theta 4 by 4 factorial. I've used different colors to mark different points, different distances in fact. Now if we'll take what is 1 plus I theta, so this is theta, this distance. If I multiply this I, it will simply rotate by 90 degree, right, in anti-clockwise sense. So here we have this distance equals this, and it's I theta. What about I theta whole square by 2 factorial, the third term of Taylor series? So third term of Taylor series, here we go, exactly here. So that represents I theta whole square by 2 factorial. We can clearly see it's negative region, so we'll go in this direction. So same magnitude leftward. Now we'll take this point, and we are multiplying again with, so this distance is again multiplied with I, right? Because I cube is there, so it will go down. And now we have again next distance, so we'll go right, and so on and so forth. Again we'll go up, left, down, right, and somewhere the answer is going to converge no matter what theta you start with, because these angles by 4 factorial, by 5 factorial also increases rapidly, because factorial is also increasing rapidly. So there is kind of, like slowly it's going to converge. So these points slowly going to converge if you start with some values, right? So now we know at the end somewhere you will end there, and that is basically the location. That's basically the location of theta with respect to positive x-axis and anti-clockwise sense. And if you add all these vectors, that's the sum total of vectors, which is represented by to the power I theta. This location is fundamentally same as cos theta plus I sin theta, which is by this route you keep on moving, and one day you are converging to this point, which is e to power I theta. So I hope, like, the Euler formula by Taylor series was not quite appealing, because we shows as sine and cos are power series of cos and sine. So we can also show this by means of this elementary argument, which is, like a visual way of understanding this Taylor series expansion. And not only this, now the immediate consequence will be now cos theta plus I sin theta. Once you know, you can write it as e to power I theta. So if you have got this guy, so this point is e to the power I theta. We have its conjugate, e to the power minus I theta. And if you add them up, they'll just add to a real quantity, which is basically 2 cos theta. Okay, so you can visually see 2 cos theta. What about this distance? This is imaginary quantity, so that's 2I sin theta. So you can see it's basically 2 sin theta and 2 sin theta. So magnitude wise it's 2 sin theta, and I means it's perpendicular to the x-axis. Okay, so some of the beautiful application for JEE problems will be in cos theta you can write now in terms of exponential definition, right? Similarly, sin theta can be written as e to the power I theta minus e to the power minus I theta by 2y. So in our next session, we'll try to take up some questions which helps us for problem solving.